Hello everyone, I'm so glad to be presenting here today. I'm Ayman Abdelwahid, a fourth year PhD student at Rotterdam School of Management of Erasmus Rotterdam University in the Netherlands. And today I'm going to present to you our joint work with RET, the main public transport operator in the city of Rotterdam, which indeed is one of the biggest cities in the Netherlands, on the project of electrifying the transit bus network of the city. This work is co-authored by my supervisors, Peter Vandenberg, Tobias Brandt, Wolfgang Ketter, as well as Judith Mulder from RIT. So when did it start? In 2016, the Dutch government announced that all public transit networks in the country should be fully electrified between 2025 and 2030. A few months later in 2017, our collaboration with RET started, and since then we have been working together on this project. It is also worth mentioning that this collaboration falls under the umbrella of the Ruggedized project, which is a big project sponsored by the European Union and aims at reaching sustainable smart cities in Europe. So our agenda for today's presentation, I will first introduce you with the problem of electrifying the transit bus networks and why is it a problem in the first place. Then I will take you through the three different phases of our collaboration with RET, starting from phase 0, which was exploratory phase, and then moving to phase 1 and phase 2, with each focusing on a different part of the city. Finally, I will conclude and summarize our findings, lessons learned, and managerial implications of our work. So let me first introduce you to the problem of electrifying the transit bus networks. So the project of electrifying the transit bus network in Rotterdam was basically about replacing the diesel bus, which you can see on the left in this photo, with the electric bus on the right. This is an actual photo taken earlier this year in Rotterdam, and as you can see, there is this charger on top of the electric bus, and these are the chargers that are used to recharge the electric buses during the day. However, unfortunately, it was not possible to directly make this replacement without making a complete replanning and restructuring for the whole network. Why? The answer is conventional diesel buses used to usually run for the whole day without needing to refuel their tanks during the day. So they go out of the garage in the early morning, operate at different lines, driving from one terminal station to another. Then at the end of the day, they go back to the garage and fully refuel their tanks in a few minutes, and that's it. They are ready for operation for the next day. However, unfortunately, this smooth and easy operation is not possible for electric buses as they have a very limited driving range compared to the diesel buses. So they cannot run for the whole day without recharging their batteries for several times during the day. So we have to install some chargers at some of the terminal stations to allow the buses to recharge their batteries during the day at the layovers between the trips. And similar to the diesel buses, electric buses would go to the garage at the end of the day and they recharge their batteries. Overnight charging is not an issue here, and they are ready for operation for the next day. So we have two main issues: limited driving range and the long recharging duration. This emerging need of recharging during the day enforced us to make adjustments in the design of the whole network at the various decision levels. Starting from the strategic decision level, we have to decide on where to install these chargers, how many of them are needed, and the recharging power as well. Regarding the trip schedule, which is communicated with the passengers, that should not be affected at all, or maybe just slightly changed if really needed. At the tactical decision level comes the bus assignment schedule, which is the step at which trips are assigned to buses, so deciding basically which bus should perform which trip. Of course, this would directly control and determine the duration of the layovers, which should be long enough at the stations with charging facilities to allow the buses to recharge during these layovers. Finally, at the operational level comes the charging schedule, which is basically deciding on when, where, and how long should each bus recharge during the day. Of course, this is given the layovers profile resulting from the previous step, and also given the infrastructure configuration. So the main aim here and the objective here should be that we guarantee certain reliability levels. So these are the steps, but who take care of the planning for these steps? So first, starting from the charging infrastructure, this was actually determined at the very early stages of the project, and it involved beside RET also the grid operator and the municipality. So we knew from the very first beginning where are the terminals, which terminal stations we are going to have charging facilities at. Then the trip schedule is also something that RET is mainly responsible for, but it should be made to meet certain service levels determined by the municipality as well. Then comes the next two steps for planning the bus assignment and charging a schedule, which are the most complicated steps. These two problems are actually interrelated. So in order to plan optimally for the network, you need to solve these two problems simultaneously, which would result in a huge optimization problem. So we decided to solve this problem iteratively. In other words, RET would take care of generating the bus assignment schedule with sufficient layover profile at the terminal station with charging facilities. Then we would take this bus assignment schedule and optimize the charging schedule. And then we also evaluate the performance of the network under uncertainty. Then we give our feedback to RET and suggestions on maybe where are the bottlenecks or any weak points in the bus assignment schedule. So they modify it according to that. And then the feedback loop goes on and on until we reach the desired level of performance. And before I start with the details of the project, let me first introduce you to the beautiful city of Rotterdam. The city is naturally split into two parts by the Maas River. So northern part and southern part. And you can see here in my background, actually, this is Erasmus Bridge. It is the largest bridge linking the two parts of the city together. And at the first phase of the project was focusing on the northern part of the city where Rotterdam also Central Station lies, which is the biggest central hub for the whole public transport network in the city. And in the northern part of the network, charging of the electric buses is decentralized. So it is planned to take place in Rotterdam Central Station, plus 6 other terminal stations around the northern part of the city. In the second phase, which was concerning about the southern part of the city, we have a different structure with centralized charging at South Plain Station, which is the largest bus station in the city. So all the buses operating in this part of the city would go to South Plain to charge during the day. But before I start with the details of these two phases, let me quickly tell you about our very initial analysis in the exploratory phase, which we call phase 0. I don't really want to spend much time on this phase, but in short, at the beginning of the project, RET's main concern was, okay, now we have new parameters in the systems that will be added, and we want to know what are the effects of these parameters on the feasibility and reliability of the networks, such as the number of chargers, the charging powers, charging strategies, the battery capacity, and also the energy consumption rate, which is how much energy is needed. So it's not really a factor that we control, but it is a very important factor because it also varies from one season to another, and it can really highly affect the feasibility and reliability of the network. So the main question that we had here, would it be feasible to keep the diesel bus schedule if we maximize the charging? So there are enough chargers for all the buses, and all buses charge at each layover, so we maximize the amount of charging. And in other words, would it the maximum possible reliability given the diesel bus assignment schedule, be feasible with the electric buses? So we carry out a sensitivity analysis with the remaining 3 factors here, the charging power, the battery capacity, and the energy consumption rate, to answer this question. To do so, we carry out this analysis. We started developing a discrete event simulation, which provides risk-free environment that we can use to evaluate the network under different settings. Later also, we will use it to evaluate it under uncertainty and evaluate different charging strategies. So we carried out this analysis with the very first 7 lines that were going to be electrified in 2019, and with 2 different consumption rates, a higher one and a lower one. And you can see here on the y-axis, we have the number of buses with state of charge that is falling below 10%, which is our critical level. And on the x-axis, you can see the potential charging power. And the 3 bars here represent the 3 different potential battery capacities that we may use. And naturally, increasing the battery capacity or increasing the charging power would lead to less critical buses. And as you can see here, even with the lower consumption rate and with the highest charging power and the biggest battery capacity, there are still few buses that are critical. So the main implication here of this stage that it reaffirmed us that we cannot electrify the network without replanning the trip assignment schedule. Then we moved to phase 1, which involved the northern part of Rotterdam. And in this phase, we started working on this feedback loop that I previously mentioned. So RET working on the bus assignment schedule, we are working on the charging schedule. And our goal here was, okay, first we want to develop an optimization model to optimize the charging schedule given any objective. And second, we want to compare different charging strategies under uncertainty. So we developed a mixed integral linear programming problem to optimize the charging schedule with 2 potential objectives. First, minimizing the number of charging events, and second, minimizing the impact on the grid. And in this phase, we adopted the first objective because RET suggested that this is an important objective for them, because less charging events would mean that the easier operation and also it can lead to better lifetime for the batteries. And regarding the constraints that we have in our system, there are many. So many, like the capacity constraints, state of a charge regulations, and constraints to keep the state of a charge within a certain range during the day, and some other practicality constraints also required priority. But optimizing the charging schedule is a time-dependent problem, and discretization is required to solve it. So our first approach was, okay, let's adopt a time-expanded network, which discretizes the problem at the highest practical resolution, which is 1 minute in our case, as the transit bus schedules are developed at the minute level anyway. So this would lead to the global optimal solution, of course. However, it also leads to a very large optimization problem that takes a very long time to solve. But since we anticipated that we may need to solve our problem in the real time at later stages of the project, so we needed another discretization techniques that can reach a good solution, but in less time. So we came up with the event-based discretization. So instead of discretizing the problem into this uniform 1 minute time slot, we sort of benefiting from the nature of our problem, at which charging would normally start when the bus arrives at the station, or when another bus leaves the station and another bus takes, which was in the queue, takes the charging slot. So as you can see in this figure, each dotted line here represents either an arrival or departure event, and also represents the end of one time slot and the beginning of another in the event-based discretization. So in this very simple example, you can see that, okay, we reduce the problem size from 12 time slots in the time-based to 6 time slots in the event-based. But the question is, how much do we lose in terms of quality of solution when we do this, and how much do we gain in terms of the computational time? And this table gives you this answer. We carried out a comparative study between the two models using two different networks with 16 instances per each network with different configurations. And this table shows you the average performance of the two models in the two networks. And as you can see here, at the small network with 9 buses, the discrete event model reached almost the same solution as the discrete time model, but in an average time of almost 2 seconds compared to 92 seconds in the discrete time. For the larger networks, the discrete time couldn't even reach an integer solution within the 15 minutes time limit that we set here, and the discrete event model can reach the optimal solution in 22 seconds on average. So there is a clear winner here, and of course the discrete event is much better than the discrete time, as it can reach almost the same solution but much faster. Now we have our optimizer, which we can use to give us an optimal schedule given a specific objective. But the next question is, how would this optimal schedule perform under uncertainty? And how would it perform compared to other greedy strategies? So we came up, okay, now we developed two different charging strategies based on the optimization model. The first one is offline optimized, and the second one is online optimized. So the offline optimization model actually sticks to the charging schedules that we developed, regardless of any uncertainties that occurs during the day. But the online one actually re-optimizes the charging schedule during the day based on whatever uncertainties that occurs, maybe in the trip delays or the energy consumption. And then we compared these two strategies to these two optimized based strategies to two other greedy strategies. The first one is first in, first serve, which of course arranges the buses in the charging queue based on their arrival time, and the lowest charge highest priority, which arranges the buses in the charging queue according to their state of charge, also with the option that a bus with a lower state of charge that is arriving can replace another bus with a higher state of charge from the charging spot, so can take its place. So we compared the two optimized based strategies to the two greedy strategies, and we also developed one more heuristic strategy, which we call here dynamic threshold based. And the idea behind this strategy is that was, okay, we want to get a strategy that is active and responsive to delays, similar to the online strategy, so it can react when a delay that occurs, but without a communication system, because with the online we re-optimize and then we need to recommunicate the modified charging schedule with the buses, so we need like a central unit to do so. But if we don't have this unit, then the dynamic threshold based can do so without can actually adapt the schedule, but without the need of central unit. And how it works basically, so drivers are given threshold cards, and these thresholds actually are based on the optimized schedule with state of a charge, a threshold state of a charge, and when they arrive at the stations with the chargers, they look at this threshold state of a charge. And if the actual state of a charge is below these thresholds, then they connect the chargers, the buses to the chargers, and if not, then they don't. So we carry out a comparative study between the 5 charging strategies by simulating 30 days under uncertainty in two different scenarios. The first one with full number of chargers, so we have enough chargers for all the buses at the selected terminal stations. And the second one with reduced number of chargers, so there are not enough chargers for all the buses. In the first scenario with the full number of chargers, as you can see naturally here, there is no difference between the performance of the first in first serve and the lowest charge highest priority because we don't have to make any decision anyway. All the buses will charge. This also means that the first in first serve and lowest charge highest priority provide an upper bound to the reliability of the system as they maximize the amount of charging. And as you can see here, there are no infeasibilities occurring at all with the first in first serve and lowest charge highest priority. In contrast, the offline optimization is the least reliable strategy with the most number of buses running out of energy per day with an average of 0.7, which is quite high. The online can fix most of this issue with almost only 0.1 bus on average running out of energy per day. And the heuristic strategy also is a good solution here, and there are no infeasibilities. However, looking at the number of the charging events here, which is the objective of the optimized strategy, the offline one and the online one as well, we can see that the number is significantly higher for the first in first serve and lowest charge highest priority compared to the optimized one and also to the heuristic one. Interesting finding here is that the heuristic strategy actually always lies in between the optimized and the greedy strategies in terms of charging events or grid load. When looking at the average minimum state of a charge here, you can also see that for the first in first serve and low charge highest priorities, they have very high value, which also reflects a lot of unnecessary charging. So, but with the optimized, the goal here with the optimized was 30%, and as you can see here, the online is the closest one to this target of 30% with an average of 28. Why the offline cannot keep all the buses close to the average? Because it doesn't react to the uncertainty and it falls to 20%. And again, the heuristic gives a very good solution here, which is again in between the optimized and the greedy. So the main conclusions from this analysis are: first, although the first in first serve and lowest charge highest priority give a very reliable option, they are not practical because they lead to big amount of unnecessary charging events and also load on the grid. Second, the offline optimal schedule is not enough to guarantee a reliable operation under uncertainty, even with planning with a minimum state of a charge of 30%. Third, the online optimization can fix that issue with the least number of charging events. And finally, if we don't have no communication system available, then the heuristic strategies that we developed here also provides a very good solution and represents actually a very good compromise between the higher reliability of the greedy strategies and the lesser charging events and load on the grid of the optimized strategies. We repeat this study again, or this comparison again, but with reduced number of chargers, and we look at an extreme case, where when we reduce the number of chargers from 15 to 6 chargers. So there are not charging slots enough for all the buses anymore. And as you can see here, the first in first serve now is a bad option, and it has almost more than one bus feasible per day. Again, the offline also is a bad option here. And the most reliable option would be the lowest charge highest priority because it has this option to a luxury to replace one bus with another bus that is arriving with a lower state of a charge. And again, the best options when we look at these figures again would be the online and the discrete time, because again, the lowest charge highest priority would result into very high number of charging events and very big grid load. So the main implications of this stage, in short, offline optimization, even conservative one, might not be sufficient because of under uncertainty. Based on these results also, RIT started building online monitoring and control system using some of our techniques that we used in this simulation. And before we move to the second phase, I would like also to mention that the first phase of the project was implemented successfully at the end of 2019, and now there are 7 transit bus lines in Rotterdam operating using electric buses. The second phase of the project, which was focusing on the southern part of the city, as I mentioned earlier, the structure here is a little bit different, and we have centralized charging at the outline station. Moreover, there is a very big area that can be used to install solar park, so there is an opportunity to use renewable energy to power the buses at the southern part of the network. And RET had three questions at the beginning. So first, what is the value of installing this solar park? How much can it reduce the impact on the grid? Second, how would installing an energy storage system also increase the utilization of the renewable energy generated? And third, how can we overcome the intermittency and uncertainty of renewable energy generation? To answer the first couple of questions, we simulated the whole year of 2018 given historical renewable energy generation profile. So, and we assume that there are enough chargers, so we maximize the amount of charging, and we also maximize the amount of possible utilization of renewable energy. Okay, so, and in another scenario, we also evaluated the performance with adding an energy storage system that can be used to store the generated renewable energy when there are no buses available to charge using the energy directly, the renewable generated energy directly. So the figure here shows the daily average values in different months for the load on the grid without renewable energy and with renewable energy and with renewable energy and energy storage system. And the line here shows the average renewable energy generated with a peak here in the summer in July. And as you can see, installing renewables can lead to a significant reduction with the load on the grid, especially in the summer when there is a lot of renewable energy generated, while adding an energy storage system has limited effect here, also as shown here in this figure, which shows also the percentage of renewable energy utilization with an energy storage system and without it. But here, so the energy storage system, the benefit from the energy storage system here is limited, but in our case, it is limited because there is a very dense bus charging profile at the outline anyway. So buses, there are always some buses that are available to use the renewable energy generated. Then we move to the next step, because in the previous study, we assumed that there are buses always charged, which yes, it maximizes the renewable energy generation, but it also maximizes the load on the grid. So we want to now we want to fix that issue, and we want to maximize the renewable energy generation, but minimize the impact on the grid. Yeah, so to do so, we need to overcome first the intermittency and the uncertainty in the renewable energy generation. So finally, we put everything together, and this is the system that we propose. So we propose using a real-time decision support system, and these are the elements in the system, and it collects data from the elements of the system, the buses, the energy source system, from the weather, from the renewables, from the grid, and then it improves the predictions with the renewable energy generation based on the real-time data, and it updates the charging schedule also to take into account any uncertainties that occurred, and then it re-optimizes the charging schedule, communicated with the operators, and we have a better charging schedule, and which improves during the day. So again, we carry out one final comparative study between offline optimization and first in first serve, again with maximum number of chargers. So again, first in first serve would have the highest reliability because it always charges all the buses, and we simulate 30 days of July under uncertainty. And as you can see here, moving from the first in first serve to the online, it actually can reduce the impact on the grid by 17%. It can reduce the day load by 41%. And moving from the offline to the online can improve the renewable energy utilization by 2.1% on average, due to, of course, the better predictions. And finally, regarding the reliability, again, the offline is not reliable, but the online and the first in first serve are reliable options. So in summary, what are the lessons that we learned from our collaboration with RET? First, it is not possible to switch from fossil fuel to electric buses without restructuring the whole network and the bus assignment schedule. Second, optimizing the charging schedule is needed and can lead to much better results. Third, offline optimization, even conservative one, might not be enough to guarantee reliability. So online monitoring is needed, and using renewable energy can significantly reduce the load on the grid. And finally, the benefit of the energy storage system or adding an energy storage system on the bus's charging load really depends on the location and the bus load profile at this location. And before I wrap up, I would like to acknowledge Dr. John Collins from Minnesota University for his contribution in the early stage, the whole RET team, and Guillermo, who was a supply chain master student from RSM in 2017. And that's all I have for today. Thank you for your attention. And if you have any questions, I would be happy to answer. Thank you.